Good morning and welcome to Promess Incorporated. My name is Glenn Nausley. I'm an applications engineer here at Promess. And today I want to talk to you about improving your assembly process using force feedback. Now, before I get too far into this, I want to let you know that if you have any questions, there is a chat box on the right-hand side of the screen. And if you ask any questions, we'll have a question and answer section here at the end. And so feel free to ask any questions you have. So what I want to start off talking about is the tools that I have in my toolbox. So here I have a standard Promess electric mechanical assembly press. This is actually a 3 kilonewton configuration. All Promess presses come standard with full positional and full force feedback. Now we get the positional feedback from the servo motor itself, and we get force feedback from the internal load cell to the press body. What this means in a simplified sense is I know where the press ram is in space and what kind of forces are being exerted on the end of the press ram. Now, when you typically think of a pressing application, most people think in a kind of a hydraulic sense. And in this, what I mean by this is people think in terms of position and not so much in terms of force. And when you really kind of think of force feedback or some kind of load cell on the end of your press ram, it's more of a monitoring process. It's more of a, we're going to move to a position, check the force, was the force good? Now here with a turnkey servo solution here, we're able to actually even use the force feedback to control where the press is moving and how the press is moving. So in a sense, the press ram or the press itself can almost feel out what it's pressing against, like a human would. If I was strong enough to press this die spring down, I could feel through what's happening and stop where it's necessary. Now, on a technical programming sense, what this means is a Promess press has 2 basic programming steps. We have a positioning move, which is a commanded position based on the positional feedback to a specific and particular spot. Again, this is the hydraulic sense of thinking. We're going to go to a specific position. And then we have a move to signal, and more colloquially known as a move to force, where we're actually going to tell the press to move to a specific signal reading, or in this case, a specific force reading. Now, pretty much every single application that a Promess press is involved in, or any Promess system for that matter, is some combination of those 2 steps. You're going to have positioning, whether through space or against a part, and then some kind of move to signal to move to a specific reading. Now, what I first want to get into is what I'm going to just call just a simple press to force, or press to force only. And now while you're actually moving against your part, it is only moving to force. So 95% of all of our press applications fall into this category. And I'm going to draw a couple pictures here just to give you some conceptualizations. So here on my x-axis, I'll have position. And on my y-axis, I'll have force. And on some kind of press or interference fit, what you'll have is a curve that looks somewhat like this, where you have the press is moving through air. It has not made contact with a part. It makes initial contact, and then there is some kind of interference. Now, depending on the part, it might not be flat. This might be angled. It might dip. It really depends on the part. But then at some point, you hit a shoulder, or you hit a bottom out, or in in my basic terms that I usually think of, you have metal on metal. You have something hard. So in this process, this press to force, we have the press move to whatever position in this area before it makes contact with the part. And then we're going to target a specific force value. Now, let's say this point right here, well into the bottom out, is 500 pounds. So what happens here is the press is actually going to go in its move to force. It's actually going to move. It almost doesn't care how far it moves. It's only going to move until it sees 500 pounds. So it's going to go through this whole process. Now, the pros to this versus an actual positioning, just a straight up positioning move to the bottom out or the shoulder position, is it's a very flexible process. And what I mean by this is if you have even slight part variations, let's say, because bearings are not always made down to a micron's specification here, you might have a bearing that is a millimeter taller or half a millimeter taller. I don't have to make any programming changes or any excessive rejects. All that's going to happen is it's still going to look for 500 pounds. It's just going to happen at a different spot. So now you have little minor conditions or little minor variations in your parts that are not going to affect your process. It allows for some flexibility. Now, one con to this, and this is really kind of a con throughout all of these techniques that I'm going to talk about here. Your accuracy is very dependent on your speed, and accuracy is always going to be in opposition of speed. The faster you go, the less accurate you are. But what that translates into is the faster you go, the further you're going to overshoot potentially on force. Now, with a bearing or any kind of press to a shoulder, usually this is insignificant. If I apply 500 pounds to a shaft, or if I apply 700 pounds to a shaft, or 550 pounds, it's not an issue. Now, one very specific example, if you haven't already picked up on it, I have a gear set here. This is straight up the easiest explanation for this is a basic bearing press. Now, here we would have the press. This would be mounted on the press ram. The press would come down, wouldn't make contact, and then look for the 500 pounds or whatever the seat force is. Now, if this was a taller or shorter bearing, again, it'll go a varying distance looking for that seat force. One other pro to this, and this kind of method, is it makes, when you do have, let's say, an egregious error or an error, an actual error, it makes things obvious. Because now, not only are you seeing less force, let's say you've double stacked a bearing. Something happened in the process, whatever. You will have a significant positional change. And this is easily picked up by our controller to say, this right here, this position is way out of tolerance. And typically when people think of this, it's, again, going to a shoulder. Sometimes the shoulder is not always on the part or a specific feature to, say, the part and the case that it's being pressed into. The first thing that comes to mind is a dowel. Sometimes a dowel doesn't actually press to a hard stop, but what can be designed is actually tooling that goes on the end of the press ram that the tooling can bottom out on the case, where the dowel will then be placed at a fixed depth into the case. And again, kind of the same thing with minor variations. A lot of times dowels, the critical dimension is the radius, not the height of the dowel. But this leads me into the next technique we have, which I don't really have a good name for it. We usually around here call it a touch point, but it's where we'll use a positioning step and a force and a move to force in combination to assemble or complete your process. So back to my graph. Again, we have position, force. And for this particular process, what we do is rather than using the force to find a bottom out position, we use the force to find a touch position. So again, back to my curve, I'm moving through air, I'm seeing 0, and then I make contact with the part. So I'll actually use a move to force to find this position. And then I will move a fixed positional amount. So say 10 millimeters. I'll move 10 millimeters more, which will probably, typically given these applications, will give me some kind of curve that looks like this. Now, we typically see this kind of application in like staking. Let's say you need to make a 10 or a 2 millimeter stake. We'll find the touch position. So now you don't have to do any kind of, you don't have to worry about if I move 15 millimeters, did I actually stake it 2 millimeters? I can just go to 50 pounds, find 50 pounds on my part, and then move 2 millimeters further. And this allows me to have a fine control over how far the press ram is moving in. Again, this adds a little bit more flexibility to the process because now if you do have minor changes, you don't have to go in and adjust any kind of blocks or find out how far more you have to go. The touch point takes that out of the equation. Now, one of the cons to this, though, is kind of the same thing with the original press of force. Speed, again, is in opposition to accuracy. The actual positioning move can fly. Once we find the touch point, you can just go 2 millimeters as fast as you possibly can. But here to find the touch point, the question is, what is the force or what forces do you need to find? Because if 50 pounds is good here, is 50 pounds good on another part? Or if I'm looking for 50 pounds and let's say for some reason it's a softer part, 50 pounds might put me here. Or if I get any kind of overshoot, it might put me over here. So this portion of the actual press becomes slower. But at this point, it's more of a marginal slower. It's still fairly fast in the whole process, but you do have to take the time to actually find it. And with kind of to go over the whole scope of the move to force, it's usually a lot of you're kind of feeling out what's going on in the process. So you need to have methods of essentially slowing down. Again, this is most commonly staking. A lot of times we might also use this might also be for, say, like a spring preload. If we want to find the touch point to, say, find the top of the spring, and then we want to compress the spring to a certain specific depth to fit into, say, like housing. So we went over press to a force, and we went over a touch point application. We also have a press to a rate of change, or I usually call it a press to a derivative because it sounds a little bit more sciencey. But back to my trusty graph of force over position. So again, every part or press application has some curve like this. Now, to go back to my high school mathematics, if I was to graph the slope of this curve, it would look something like this. We have a rate of change of roughly 0 while I'm not making contact with the part. I get a slight bump in the rate of change when we actually make contact with the part. And then it goes back down to 0 or follows the slope of the curve again. Depending on your part, this might actually be slightly slanted. And then we get a bottom out. Now, the advantage of this is this rate of change curve looks the same no matter if I'm seating at 1,000 pounds or if I'm seating at 2,000 pounds or if I'm seating at 10,000 pounds. The curve should be the same. Now, this leads into the first reason, or the first kind of reason I usually stick to, of why you would want to use a rate of change. Rate of change is very flexible as far as handling press interference fits. So if I have, for whatever reason it is, I know my part's going to seat. You know, at some point it's going to shoulder out and it's going to stop. I just don't know if it's going to shoulder out at 1,000 pounds or 5,000 pounds. This allows us, rather than say setting a specific force, which is usually the first thing the first question is always, when you see this, if I know it's going to seat, whether or not it's 1,000 or 5,000, why don't I go to 6,000 pounds on everything? This should handle the issue. If I go to 6,000 pounds and it seats at 1,000, it's just going to shoulder out, and the 5,000 pounds is just going to go into the shoulder. Well, we had an application like this. Specifically, it was a wheel hub. We were pressing studs into the wheel hub. Now, again, a stud is going to shoulder out on the wheel hub. You can see it visually. You know it's going to bottom out. What ends up happening, though, is, for, again, part manufacturing tolerances, the interference press fit force is all over the map. Variations in thousands of pounds sometimes. If we were to go through, and we did this on the first handful of iterations, if you go through and apply 6,000 pounds on each of these studs, it actually begins to deform the hub, or any of this excess force starts to go into the hub and starts to deform the hub. So yes, the stud was bottomed out and shouldered out, but now we've created a secondary negative effect that we wanted to try to avoid. So by using a rate of change, what you're able to do is find that bottom out point, regardless of where it's at, and stop and not apply much more force than is needed. The other situation, which kind of echoes that you would want to use a rate of change for, is a part that is delicate. We've had a few applications where, as you're seating it, everything is fine. But if you more than, say, 100 pounds on the part after it's been seated, you'll crush or destroy or damage the part in some manner. And a rate of change is used to give you the most accurate point where the part has bottomed out or shouldered out. And this kind of leads back to my whole a lot of the cons related to this is related to of how speed and accuracy are opposed to each other. And here, even more so. Because of this, rate of change has to move slow. It has to deal with a lot of information. So a lot of times, you need to have very particular reasons why you want to use this to have it be a good decision. For instance, you can theoretically program a bearing press to press a bearing on with a rate of change, but usually it's over engineering. The bearing is not a delicate part, or delicate in this scale of forces, and the need for the delicacy doesn't outweigh the speed loss or the potential loss. Now, the other con to this is it's a little bit hard to wrap your head around. And I always think of it as like a cognitive load kind of thing. For a move to force, I can explain to an elementary school student, hey, this press is going to put 50 pounds onto this part, and it's going to put this bearing onto the shaft. And 50 pounds is a very easy thing you can conceptualize. I mean, I'm saying it now, and you're probably thinking of 50 pounds immediately. But what if I told you we're going to be pressing to 500 pounds per inch? Now, you probably have some grasp of what's going on, but can you actually visualize or really conceptualize what 50 pounds per inch means in a quick fashion? And what this translates to into a process sense is, let's say you need to make a change, or you had a part or a tooling redesign or a part redesign or some kind of situation where you need to change the process. You now have to go through and rethink in terms of newtons per inch in this instance, or pounds per inch, what you need to do. And it's little, but on top of everything else you usually have to do in your day, it's just that much more you have to do. Now, one thing to kind of talk about another application and kind of give an example of this. I've been focusing on the bottom out portion of this. Now, most parts also have the touch point. Now, let's say you have some kind of application that you're actually pressing. You want to make sure that something clips in. Or let's say there's a snap ring. You want to make sure the snap ring snaps into place. We have done applications in the past where we would pay attention to the rate of change, and we'd focus on when the slope went from a positive down to a negative, so we can catch this point right here, right when it snaps into place. So the one other advantage to a rate of change is you can find some very specific part features. Now, that's kind of the end of what we have for rate of change. One thing, and really, to go back to what I was saying before, all of these moves are in some combination of positioning and a force move. So it's a little bit of a Lego. It's a little bit of a Lego set. We've used multiple positioning moves and multiple force moves in one process before, and it really depends on the part, on the features and the natures of your part. And one last thing before I get to the questions and answers here, this is only really the tip of the iceberg, because we've also done applications where we press to the summation of multiple load cells. We've had, say, an application where we had 2 load cells on it, and we were pressing to the difference between the 2, and that value needed to be a certain amount. We've also pressed to certain. We've pressed to a certain value on, let's say, like flow meter, and really any kind of, again, going back. In our terminology, it's a move to a signal, not necessarily a move to a force. If there's anything that can provide a signal to us, we can press to a certain value on that signal. And again, we've done flow meters, we've done voltmeters, things like that, where you press to a certain value coming back from the part. Now, that's all I have for right now. So let's move on to questions and answers. So again, if you have any questions, feel free to put them into the chat box on the right-hand side. And we'll get to them from here. So the first question we have is how close to the target force does a press get? Now, I kind of alluded to this a little bit when I was talking about the press to a force, where you have a little bit of an antithesis with speed and accuracy. Now, what I really mean by this is at some point the press needs to stop. So if you're moving faster, so let's say I'm targeting, I want to go to, let's just make the numbers easy, 100 pounds. If I'm moving at, say, 0.5 millimeter per second, to find that 100 pounds, the press is going to crawl. It's going to go super slow up to that 100 pounds, and it's going to probably hit 100.1 pounds, just as a for instance. Now, if the press, which these presses are rated to go, or a standard press is rated to go about 200 millimeters per second. Let's say I was going 200 millimeters per second. It's going to fly. And like a semi-truck going into a wall, it's going to see the 100 pounds hit the brakes, but at that point, it's not going to be able to stop that quick. And you're going to overshoot to, say, 500 pounds or more. At 200 millimeters per second, it'll probably go much more than that. But the point being, depending how much overshoot you get from your target depends on how fast you're moving. And again, this goes back to that delicacy thing of, can a bearing onto a shaft can survive a few extra 100 pounds of force if necessary, where, if I'm on the wheel hub or anything, if I'm going over on force, I'm actually potentially doing damage. So a lot of times it depends on your part on how fast you can move and how accurate you can get. Next question is, can you press to a position and a force at the same time? It's a good question. So one thing that I completely didn't talk about in this whole talk is monitoring. I've only talked about using force to actually affect the position of the press. Now, our press systems have full monitoring capabilities. So on top of being able to control and move the press to these certain values, I can actually even just monitor or graph or trace what force I'm seeing and what position I'm at. So while you can only ever command to one at a time, so I can only do a positioning step, or I can do a move to a signal or a move to a force, you can monitor over both. And this is what usually happens with a lot of times for your pass or fail criteria, where on a move to force, if I'm pressing in this bearing, I'm actually monitoring, I might be moving to a force to find the shoulder point, but my pass fail, or usually the most important pass fail, is how far did the press actually move? Because let's say I get a very, a machining mills, the lathe is getting kind of worn down, and the diameter of the shaft is much larger than it should be. I'll still hit that same amount of force, but I'll be much further off from the part. So you can actually monitor over position and force at the same time to get you a more accurate in-process pass or a fail. So the next question is, how is rate of change calculated? There are some settings like how many points, and sometimes the rate of change value is a little bit delayed comparing to the force distance curve. So how we calculate the rate of change is essentially we do on a default level, we do essentially the difference between each point that we collect as far as force goes. Now, depending on how noisy the curve is, we can kind of delay it. But essentially, we're calculating as the data points are being recorded on the signal plane level, we're taking the delta from point to point. Typically, again, we have the ability to kind of give it a, take an average over 50 milliseconds for a point, but that kind of depends on the part. Some parts are really, if you got a lot of chatter. So one thing, and this kind of permeates the entire discussion, but even though this might be what every part looks like on a kind of abstract level, in reality, it's probably closer to that. And then at that point, your rate of change would have a little bit of a flutter to it. And we have some kind of, essentially it's a sampling rate where we can adjust how fine-tuned that is. The next question is, how fast can you press with a move to signal? So my rule of thumb, and generally, there are a few exceptions to this, but my rule of thumb is if I'm expecting a bottom out, 5 to 10 millimeters per second is the fastest I would go. Now, if you're pressing against something that's really springy, something that's not necessarily going to bottom out, like say a die spring, I've had good results up to 20 millimeters per second. But it depends on your part. And one thing with all of this, seems that my interference fits get smaller and smaller every time I draw these. Now you need it. Typically 5 millimeters per second is my first. If you call me up and say, hey, I've got a bearing and a shaft, my first recommendation is try 5 millimeters per second. Because that'll give you decent results at a decent speed. Now, if we come to find out that your part needs to go much, much slower, I talked about doing a move to force and then a positioning move. One thing I didn't quite touch on is we can also do the opposite of that. We can do a positioning move into the part and then do a move to signal. So we do have a lot of applications that say you need the accuracy, and it has part characteristics that you need to go slow, but we can do a positioning move to this point. So I can go 20 millimeters per second, 30 millimeters per second, something fast into the part, get the bearing most of the way on, and then slow down and go to our target force. So again, it goes back to my talk about these are a lot of Lego pieces, and I can build up my castle how I want to. But typically 5 millimeters per second is where to start. So the next question is, how do you determine a position or a force program is the right for a process? So my thought process is, the first thing is, what's your critical dimension? If you pull out your spec sheet, what's on the spec sheet and says this is the important part. Now if you come out and say this this bearing needs to be pressed 10 millimeters. My first thought is, let's keep it as simple as possible. Let's do a positioning move. Now, if your spec sheet says, I need force, or I need to see a certain amount of force, then my first knee-jerk reaction is, let's press to a force. Now, that's usually not a 100% telltale reason, or a lot of times that process changes 2 or 3 iterations in, but that's the first spot I start at. So, and then the next thing I really look at is, after we've pressed parts together, what does your force curve look like? Are you pressing to a spring where you're kind of just going up in a linear fashion? Or is it an actual interference fit? If it's an interference fit, I tend to want to go with a press to a force, because that way I know I've hit a shoulder point, or I've hit a specific criteria on that interference. Now with a linear, a lot of times I want to go to a position, because I want to go to a specific position, and I probably want to see, typically if it's linear, your spec probably asks you, okay, we went 2 inches. What is this force value? If that force value is 1,000 pounds, it's good. If it's 1,200 pounds, it's bad. So it's a little bit of a combination of, what is your critical dimension? And then what does the part just look like? Those are usually the 2 things that dictate what kind of process I want to go for. And then again, the things that don't really show up in the programming is, how delicate is the part? How delicate, how much money is it worth? If it's delicate and we don't want to potentially destroy it because it's, a 24 karat gold bearing and you're going to destroy it, then we don't want to, we'll take different approaches to it. But again, critical dimension is usually the very first thing to think about. So I know there's a few more questions we didn't have time to get to. I want to thank you guys for tuning in. Feel free, if you have any questions, you can contact us. The contact information is on the screen. You can also contact us on our mainline phone number at 810-229-9334. And also feel free to drop any questions you have or have any discussions about applications on our website. So thanks for attending.